Okay, so I am finally starting physics and more specifically electricity or electromagnetism, because this is probably, in my opinion, not the best area of physics and also one that people struggle with quite a lot. So to start with, I'm just going to go through some basic definitions, namely charge, current, voltage, resistance. I'll make a separate video on each of them going forward, going into more detail, Kirchhoff's laws, how to add them in series, parallel, all that kind of thing. But for now, I just want to get the very core ideas of what electricity is and what these four main terms mean, and anything else along the way. So, very simply, what is electricity? Well, if I take any particle that has a charge, so it could be an electron, it could be a proton, it could be a sodium ion, just anything that has an imbalance of electrons and protons, or more generally, an imbalance of charges. So for example, an electron. If I take an electron and I make it move any which way, I've generated electricity. And that is more or less it. Electricity is simply taking a charged particle and making it move, usually with a couple of buddies with it as well. So, how do I do this? Well, that's a bit too far for today's course. Might be with a battery, might be with some electromagnet. But the idea is, as long as I make them move, I'm good to go. So if I imagine just a simple circuit, I'm just going to have a simple circuit with a lamp. I will also have a very specific video, probably the next one, explicitly about circuits, how to read them, how to draw them. But in this case, I'm just going to draw a simple circuit that is a wire containing moving electrons or moving charged particles, but we'll stick with electrons just for the simplicity of it. I have a cell, so like a battery, half a battery, that pushes out these electrons, and I have a lamp that's going to be lit up. Nothing too complicated. First of all, why do I need a wire? Why can't I just push electrons through anything? Well, technically I can, but different materials allow electrons to move through them in different ways. And this is actually the first definition I'm going to come up with. You probably wouldn't have thought that I would start with this, but it is this idea of resistance. So, I want to make things move. Resistance stops them moving. Seems fairly self-explanatory. If I want an electron to move around this circuit, I want it to move as fast as possible, as freely as possible. I don't want it bouncing off of loads of things. I don't want it getting stopped or slowed down or reflected backwards. Yeah? And that is this idea of resistance, just stopping the flow of a charged particle. So why do we use wires? Well, wires, typically made of copper or some other metal, have a very, very low resistance. It is easy for a charged particle to move through something like metal, less so than something like cloth or plastic or wood. They will still move between those, make no doubt about it, but it will be harder. They have a higher resistance. So, what exactly is charge itself, this thing that we're moving and then stopping from moving? Well, charge is, for now, just an intrinsic property of something. By that I mean, something just has a charge. It's a bit difficult to explain what it exactly means, in the same way it's a little bit difficult to explain to someone what a mass is. Like, yes, you could say that a mass is how much stuff is inside of something, but it's still an intrinsic property. Everything has a certain mass. I can change the mass, just like I can change the charge, but it still has it. Everything still has it, or zero of it. So charge is just this intrinsic property that when moved makes electricity. Now, let's say I want to watch these charged particles moving around. And in particular, I'm stood at this corner of my circuit and I want to see how many electrons go past me every second, right? Remember, it's all about these things moving. Everything is about these things moving. So I stand here with a stopwatch and I count how many electrons go past me every single second. That would be a reliable indicator for how much electricity I have. The more electrons I have flowing past me every second, the more electricity I'm going to have. pretty self-explanatory. This idea here of charge passing per second is called the current, which is another key word. The current is just the amount of charge that is passing round the circuit every single second. If I stood here with a stopwatch, how much charge is passing me per second? That is my current. You may have heard analogies to do with water. So current would be the amount of water flowing past a point. I try and stay away from those kind of analogies. I've worked with a few over the years with things like army men and ants carrying things and water flowing, and I basically find that nothing really works that well with it. I think it's best just to recognize it as to what it is. It is charged particles moving. Let's watch how they move. So current, how many of them go past every second? The more current, the more electricity. Fairly self-explanatory. If I increase my resistance, I decrease my current. Not worrying about any equations for today, but again, pretty self-explanatory. We're just thinking about how these things move. Right, now for the weirder one, or the harder one to try and explain, which is, I'll draw it in the middle, voltage. Now, there are lots of different descriptions for voltage, and in fact, voltage almost peels off into two separate categories, one being EMF and one being potential difference. But in reality, they're all more or less the same thing. They just operate at different points in a circuit. So what exactly is voltage? Well, some people might tell you that it is the force that these electrons are being pushed around the circuit with. Some people might tell you it is the energy that these electrons are providing to things in the circuit. So which one of those is true? Because something can't be both a force and an energy. Well, the answer is it's neither. It's voltage. It's its own thing. It's not a force. It doesn't work the same way that a force does, but it's also not energy. It's not necessarily a certain type of energy going around. That would be electrical energy, which is why it's got its own name. It's got its own SI and base units, and it's its own thing. So what exactly is it? Well, the formal definition is it is energy per charge. How much energy do each of these charges have? And it does go into a little bit more complicated than that. But the way that I like to think about it, and if any of you have a physics degree watching, not sure why you would, but I know you'll be quick to correct me. But a nice way that I like to think about it is simply the amount of energy that a charged particle gets and then transfers later on. When an electron is sat in a battery or in a cell, it's doing nothing, it's not moving. But when we turn on the circuit, we need it to start moving. And in order for something to start moving, we need to push it and give it some energy, which is where this idea that voltage is a force or an energy come from. People say it's the force to push it or it's the energy to push it. Really, it's neither. But we can think of it as the energy that charged particle is given in order for it to start moving. So this electron trundles along, he has his energy with him, his voltage, his energy per charge, and he travels around the circuit and he gets to my lamp. Now, this lamp doesn't really care if something runs past it. Right, if this electron just flows through it, it doesn't really care. Like, it's just a particle moving past it. What it cares about is the voltage that this particle has, or the energy that it has. Because this lamp, in order to turn on, they need some energy. Where do they get that from? The moving particle. And that is what voltage is. It is the amount, almost, of energy that a component requires for it to work. So my electron picks up some energy from here, travels along the whole circuit, and almost deposits some of that energy inside the lamp. Again, it's not a perfect analogy. The actual concept of voltage is a little bit more complicated. But in essence, you can visualize it that way. He's picked up some energy, he's carrying it along, and he's depositing it in a lamp. And now that lamp is working. Again, in a special video about voltage, I will go into more detail about this. But the reason that I put a voltmeter around a lamp that looks like this, I measure voltage by taking a specimen before the lamp and taking a specimen after the lamp, is because the electron has a certain amount of energy here, deposits it in the lamp, and then comes out of it with less energy than it started with. And that change in energy, that difference in energy, is a difference in voltage, or a difference in potential, a potential difference. Again, very tricky to kind of get your head around. But a voltage is its own thing. It is the energy per unit charge. It's not a form of energy, it's not a force. In fact, it's probably closer to a type of pressure. But for the purposes of basics starting out, we can think of it like that. I feel like I've been on a bit of a long-winded rant about voltage, but it's weird. It confuses a lot of people. As I said, I will be making a video going into a bit more detail on voltage in a few, along with the rest, but this is just a very bare bones breakdown of what exactly is electricity.